Hello all and welcome to Sanders Amplification. I want to present a tutorial that I hope will help amp builders understand some of the core principles of AC and DC currents and how they function in a very simple tube amplifier design. These principles probably apply in many other areas too, but it took me a long time to learn how these worked, and I went on many forums, read books, and I couldn't really ever get a clear explanation. So I'm presenting my version here, and if you think I'm wrong, well, good-o, that's fine. I'm only doing this in the hopes of helping others who, like myself, were unclear on certain really key principle concepts. And I suspect that a lot of people don't really understand this fully, but who knows, maybe they do and it's just me. But here we go. So we're going to start with DC current. DC current flows from negative to positive. Historically, the plate was considered positive and the cathode was considered negative. So positive plate, negative cathode, positive plate, negative cathode. And we still think of this as being B+, the positive. But actually, we finally figured out that DC current flows in the opposite direction than we initially thought. That is to say, it flows from the ground up through the tube toward the plate. So our current is actually going from the chassis to the center tap, through the center tap, cycling around through our rectification, whether it's tube rectification or diodes, and turning into a DC voltage. Of course, we have 120 volts of AC alternating current coming in here and powering up our power transformer. And depending on the winding ratios between the primary side and the secondary side, that will determine what kind of voltages we're going to have on the secondary side. So we have 120 volts coming in here, goes through a winding, creates an electromagnetic field, and creates an output voltage on the other side. So we only have 120 here, but by the time we get through our rectification, our AC voltage has become a DC voltage. It's been rectified, turned into a direct current here, and we could end up with 350 or 450 or 550 volts of DC potential in our amplifier. And the voltage we're going to end up with here is determined by the winding ratios here and the resistance in our dropping resistors. Now, I'm not going to get too deeply into power filtering or the design of power filtering and the size of these resistors and the size of these filter capacitors. I'm really interested in explaining the current flow, because this is really key in understanding, sort of standing back from the amplifier and really understanding just the basic principles, which, while I could find out all sorts of amazing details and try and grapple with a huge amount of math, I could never get a clear explanation of just how this thing holds together and why it works the way it does. And so here's my best attempt. So DC voltage is a potential voltage, and I believe it's called that because really the DC voltage doesn't move very fast. We think of current as zooming around all the time, but DC voltage moves very, very slowly. It takes hours and hours to cycle. All of the DC voltage wants to go to ground as quickly as it can. We know this because we know that if we stuck our hand in one while it's plugged in, it'll go to ground straight through us. It'll be very happy to go to ground, and we might die as a result. So we understand not to short these things out. So there's this big load just sitting there, and we're controlling it. It can't really go anywhere. very much, because we're controlling it with resistors and capacitors, and we're deciding what that DC voltage is going to do. So here we have this potential, this loading that comes up through our nodes A, B, and C. You could have more depending on your amp, and you could have a much more complicated amp design than this. But we have a potential sitting there. And then on node B we have a potential coming up and sitting on our screen grid. And then through our C node we have a potential coming up through a 100k resistor and coming up and sitting on our plates. And this is also being powered by the C node here. So that voltage is just sitting there on the plates. And so what is happening is that our voltage, the current cycle of the DC, is coming from negative to positive up through our cathode resistor onto the controlling the cathode, and inside the tube we have something going on. We have heaters here, or filaments, you could sometimes call heaters, sometimes called filaments, being powered by a 6.3 volt winding. And again, the voltage is determined by the winding ratio here. Very different winding ratio going on here than we have here. Very different. This is putting out hundreds of volts, this is only putting out 6.3. So that heat on the filaments here means that these filaments heat up to a considerable temperature. I've seen writings that say it's up to 1,000 degrees. Anyway, the heat excites the cathode, and the cathode emits electrons, and so they want to be, once they're free in here, they want to go up to the plate. And what we have happening in here is that tubes are vacuum sealed. You can tell when the vacuum is lost because quite often a tube will turn white on the inside, and the vacuum will, the tube will stop functioning, because the DC, if you just have this DC current out in the ordinary air, there's a lot of resistance in the air and the DC will not travel through it. But through a vacuum, it's happy to go up to the plates. And in fact, it's so happy that within this vacuum, the electrons travel at extremely high speeds from the cathode up to the plate. Extremely high speeds. But that's the only place the DC is really, moving at any rate, especially compared to the AC, the alternating current. We have a guitar signal comes in and we hear it almost instantly. It seems instant out the other end. Where you bang on that guitar and shazam, it's amazing. So the DC is moving very slowly elsewhere, but in the tubes it's going shazam, 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 shazam. That's a technical term, by the way. Anyway, so what we're doing here is we're injecting our signal voltage of AC, which could be 1/4 of an amp, possibly less, possibly a little bit more, but not usually much more. We're injecting that in here, and it is getting a free ride on top of the DC. If you look, imagine this is the screen on an oscilloscope, and it has two channels, and one of the leads is plugged into the DC, which is direct current, and it will give us a straight line, a flat line, because it's just direct. And it will read off at whatever the voltage is that it's reading. The AC current, if we connect a lead up to an AC line, that will always float. It looks like, if you watch it, it looks like it's just sort of floating there above the DC current. And it's quite often represented as a sine wave, because AC, in fact, is very complicated coming out of a guitar. We don't just have a single 1K note, or like an A440 cycles per second. We've got bass, which is going to be big. We've got very, very small high frequency, and we've got mid-range. So coming out of a guitar is a huge range of sound waves, and when they come in here, they don't look like a pretty little 1K sine wave. But what does happen is our AC comes in here, gets caught up in this rush of electrodes going up to the plate, and gets amplified with it. Gets caught up because they're going shazam, shazam, shazam up to our plates here, and the AC gets amplified and carried up through this wiring and on its merry way. The way the AC behaves is determined by the way we have loaded the circuit here with DC and the way we're controlling it with these particular resistors especially. So we have our cathode resistor. It's typically a 1.5K resistor, and we have our plate resistor, often also called a load resistor. So here we have our voltages sitting on our nodes, and here we have our C node, and that is supplying, because of this 100K resistor, we're dropping it down to 200 on the plates. So the relationship between this resistor and the plates is very important. That's why this is called the load resistor. And the relationship between the cathode, how the cathode behaves, and how much it's going to release electrons, is dependent on the size of this resistor here, the cathode resistor. So typically we would see a 1.5 on many typical, like a 12AX7 tube or 12AT7. It's very, very common to see a 1.5 resistor. So let's go back to potential for a minute. We have 325 here, 200 here, 200 here. The higher this voltage, the higher potential we have in any of these places, the more it wants to go to ground. So imagine this is 1,000 volts. We're going to be we're careful with 300 volts, so we're going to be extremely careful with 1,000 volts because that'll just knock you down dead, right? If it's only 9 volts coming out of a battery, well, you stick that on your tongue when you're a kid just to get that little electric shock, and it doesn't kill you. Surprise, surprise. It still is discharging through your tongue, but I don't advise doing that. It just leaves a nasty metallic taste in your mouth. But so we can think of potential as, you've got 1,000 volts here. It's looking for somewhere to go, and that's essentially what lightning is. It's building up in the atmosphere, and then it finally finds a path to ground, and shazam. So moving along, I look at the DC voltage as an invisible platform throughout the circuit over which the AC rides. It floats on top of it. And they're quite separate. They don't mix and mingle. You might think the two would mix and mingle, but once they're separated in here, they can't go the same places. For example, our AC current will get amplified here and pass up through here, and it will pass through our capacitors. But the DC load that is sitting on here is also sitting on here, and it's coming to that point, and it's passing through this and coming to that point and down to this point, but it can't go anywhere. All dressed up and no place to go, because capacitors, simply by the physics of what a capacitor is, block DC voltage, but they allow AC to pass through. So we have what is called a slope resistor here. I was working with somebody who accidentally put a 100 ohm resistor in here instead of a 100K resistor, and the amp, when we fired it up, had no treble control. The treble pot did not work. And that is because the signal goes to the path of least resistance. A 100 ohm resistor here is nothing. It came zooming down here, right through here, and right through here. It was very happy to do so. But when you put 100K in here, the signal is more likely to want to simply pass through this capacitor here. So anyway, only the treble can get through this capacitor because it's a very, very small wave, and 500 picofarads or 250 picofarads only allows very high frequencies to pass, and they are then controlled by the treble. Next down we have bass. Resistors tend to allow bass to pass through much more easily than treble signals, just sort of as a rule of thumb. Don't quote me on that. It's not a very good definition, but our treble is passing through here, our bass and mid-range is passing through here, and we might have a large capacitor here. It could be a 0.1. Let's just call it a 0.1 here, and a 0.046. I've got that round the wrong way, I think. 047 and a 0.1. So these allow base signals and mid-range signals to pass through, and we have a resistor here that will allow some of the mid-range to bleed off to ground, and our treble's coming through here, our bass is coming through here, and lo and behold, our signal gets sent to the next stage. We have the same thing happening on V2. Now I should mention that this diagram has these tubes with the plates drawn in parallel. If you're wondering why it looks a bit odd, here's something that is not in parallel. But this is like a 12AX7 that has been drawn in parallel, so both plates are connected, and both cathodes and both signal grids. So just ignore that. It could just easily have been a simple half of a triode here. So we have our signal comes through, and then the amplified signal comes through here, it gets modified, and then passes on to our next stage. Really, what a pot is a variable resistor to some extent. It either lets some of the signal bleed to ground or sends it on its merry way to the next stage. So when we have a lot of signal coming through here, when this is turned up to volume, full volume, so all of the signal is coming through, and we are more likely to be overdriving this when we have a big signal coming through. It'll be sending more signal than this tube can handle. It's sending in a big wave, and this is magnifying it enormously, so we get a big signal wave that's been amplified back here, and then by the time it gets through this, it'll be reduced, but it'll still be big compared to what was here, and so that means that we're going to get breakup. It's going to exceed the specs on here. Whereas, and you know, we design amps so that they will have a certain amount of breakup. We like it. It's a nice, pleasing tone. Whereas when you turn it down, you lose the breakup, and it's a much more controlled signal coming in here. Again, we have the DC voltage loading the plates connected to node C, and it can't go anywhere because we have a coupling capacitor here. There is a lot to be said about the size of coupling capacitors and how you voice the amplifier. Same with the choice of capacitors in our tone stack. This is just a typical treble bass Fender style tone stack here. But we can change the size of coupling capacitors. If we have a very big one here, it'll allow a huge range through, and then we might end up with kind of a flubby bottom end coming out of our speakers. As people sometimes complain about 5E3 speakers sort of having a bit of a woofly bass that interferes with the tone, and that's because they have a 0.1, and if you reduce this to a 0.047 or a 0.022 microfarad, it'll filter out all the bass, and so you'll get a nice tighter mid-range tone coming through. We have a load resistor and a cathode resistor, and these determine how the tube will behave when the AC signal is injected into it. Also of interest is that when we bias a preamp tube to be hot in order to create breakup, we're actually sending increased current to the next stage, which overloads the next stage. We can have a smaller plate resistor, which would actually allow a higher voltage potential here, but in fact that will allow more signal to escape past it and drain out to ground, and it will literally come this direction and drain out to ground. So what we tend to see on a high gain stage preamp is that if we have a larger than usual plate resistor, say 200 or 220K, we will have less voltage here on the plate, but the resistor will resist much more of the AC current. It'll stop any signal, it'll force all the signal to keep going this direction, it won't let anything past. So it'll come over here and overdrive this stage. So it's interesting when we talk about biasing a tube with the load resistor and the cathode resistor, we're getting more signal out of it, but that actually overdrives the next stage. So we also have our cathode resistor here, and the cathode is people often talk about cathode resistors in terms of biasing the tube, and the size of this cathode then determines the flow of DC electrons up onto the cathode, so that the availability is greater or less depending on this resistor here. We can also talk now about the bypass capacitor. So the Brits call this, we call it a tube, they call it a valve. And it's interesting to see it as a valve because it's almost like a faucet. And this is really the tap, the control that turns the faucet on or off. If we put, a high rated here, we would get much less flow through this cathode resistor. So what we actually have is a 1.5, which is fairly standard on a lot of preamp tubes, and we have a bypass capacitor. So how the bypass capacitor works, this is kind of a fun experiment. If you have ever experimented with an amplifier while it's powered up, hopefully in a very safe manner, and attach and connect and disconnect this, you'll hear a drop in gain when it's disconnected. There's usually also one down here on our power tube as well. It allows a lot more gain in the tube. And why? Responds because it's an AC path here. It's in resonance to some extent with our AC signal coming in. It's understanding almost and interpreting the different sine wave signals that are coming in here. And this capacitor allows some freedom in the way these electrons can zoom according to the signal that comes in. The size of this capacitor can be changed enormously. A standard size is 25 microfarads. It's quite common to see a 0.68 microfarad in some Marshall preamp stages because they don't want bass. They want a bit more warmth and they want maximum gain. But if you have a big capacitor here, you allow a lot of bass movement to go on in the signal here, passing it through these stages. And typically for an overdrive stage, you don't want necessarily a lot of bass because it will make the outcome kind of flubby at the end. So basically you can dial all that down to just being mid-range gain or treble gain or whatever you want, rather than having bottom end gain, which can get very muddy and not sound so great. So let's have a quick look at our output tube for a minute. This is a single-ended amp because it has only a single output tube. If it was a push-pull, it would have two tubes, and instead of having a driver here, we would have a phase inverter, which would have a signal coming off the plate and a signal coming off the cathode. These are 180 degrees out of phase, and so while one tube is pushing, the other is pulling, and vice versa. So we get AC signals coming this way. And when we bias the power tube, the size of this is very important because, again, it either clamps down and controls this tube very powerfully and limits what it can do, or you put a smaller one in and a smaller resistor, and you'll get all sorts of things going on. And in fact, if it's too small, there's a high voltage here, we've got a big signal coming through, and it can run away and overheat and burn out, and this is where you have red plating. And that's usually in this kind of design, which is called a cathode resistor bias. Then we choose the size of this resistor very carefully, and the capacitor, bypass capacitor, acts in exactly the same way as it did in the preamp stage. You don't usually see a bypass capacitor on our driver because we're really intent on just driving the signal that we've created here straight into our tube. We don't necessarily, you'll get a lot of overdrive. You might get too much gain here, and then you're going to be sending basically a high gain signal always in here, and you might just get, all you might get is distortion, or you might get too much breakup at a very early age. So here we see again, I'm going to remind you, there's this voltage potential DC all the way through the amp. our AC is riding over top of it all the way through, passing through all the capacitors and all the coupling caps, and it comes into our output tube. Now there's a relationship between the output tube and the cathode resistor and the output transformer, just as there is in any of the other tubes, except what we have here is we have an output transformer taking the place of a plate resistor. This is our load here. This decides what the load is on the plates. This determines the loading on the plate. So we have a balance going on between the output transformer, the output tube, and of course we have a speaker here. So imagine that this is a speaker, and we would have an ohms rating on here. That could be 8 ohms or 16 or 4 ohms. And there's a relationship between these three things that when we get them in balance, it's perceived that we get the most pleasing harmonic tones, etc., etc. But you can experiment with these things to your heart's delight. And you will know that some output transformers may have several taps, which means they just have a winding that comes up, and at a certain point they take off a tap and a bit more, and so on and so on. And that's an exercise in winding ratios, exactly as we saw down here. So the point really I'm trying to make here is that we have a DC current, but it's really just sitting there. And it's a potential voltage. It wants to go somewhere, and it's moving very, very slowly. A lot of stuff going on here, which is probably what's making it move at all. But it's more or less sitting there like an invisible platform that the AC can sort of bounce along over top of. So I hope this has given you kind of a layman's overview of AC current versus DC current, and how they perform in the amplifier, and how they act together in concert inside the tube to create the little miracle we call a guitar amp. I sure hope that's been some help, and I hope I haven't rambled too much, and keep on keeping on.